Hey everyone, here's our presentation on hydropower, presented by
Sophie.
Sunny.
Marcus.
and Tanner. There is a long history of people using running water from streams and lakes to produce mechanical energy. The first instance of hydropower dates all the way back to the Greeks. They used water wheels to grind wheat into flour. This water wheel started to be improved upon in the mid 1700s, but the first notable difference was in 1880. During this time, a dynamo driven by water turbines was used to provide arc lightning, a technique used when an electric spark in the air between two conductors produces a light. By 1881, a dynamo connected to a turbine in a flour mill provided street lighting for Niagara Falls, which used direct current technology. This breakthrough of alternating currents allowed further generated power to be transmitted longer distances, which is still being used today. Later on, by 1920, the U.S. Army Corps of Engineers was authorized by Congress to build hydroelectric plants, making hydropower the fifth largest electric supplier in the United States. By 1935, the Federal Power Commission's authority used hydroelectric projects to be built by publicity or private-owned utilities. In 1936, the Hoover Dam was built, and in 1940, President Roosevelt's New Deal construction programs helped hydropower become 40% of electrical generation in the United States. In recent times, hydropower is responsible for over 52% of the United States renewable electricity generation. So what exactly is hydropower and how does it work? The source of hydroelectric power is water and running water. This is why you see most hydroelectric power plants near or on running bodies of water. The three types of hydropower facilities are impoundment, diversion, and pumped storage. Impoundment hydroelectric power plants are the most common. Typically, this is when hydropower systems use a dam to store river water in a reservoir. Then it releases this water slowly, spinning turbines in the system and activating a generator to produce electricity. A diversion power plant uses the same hydropower system as an impoundment plant, but it only channels a portion of the river through its turbines. Finally, the pumped storage hydroelectric power plant works like a battery. It stores the electricity generated by other power sources and saves it for later. When the demand for electricity is low, the system pumps water into a water reservoir of higher elevation, and when the demand for electricity is high, the system slowly releases water back through the system, spinning turbines and generating electricity.
Here's an example of a hydroelectric dam. So the water starts out in the left of this diagram in a reservoir, and then the water flows through an intake screen, which is made to filter out large debris, but it also allows smaller fish to pass through it. Then the water travels through a large pipe called a penstock. Then the force of the water spins a turbine at low speed, and this also allows fish to pass through unharmed.
Inside the generator, a shaft spins coils of copper wire inside a ring of magnets. This creates an electric field, producing electricity. Electricity is sent to a switchyard where a transformer increases the voltage, allowing it to travel through an electric grid. Water flows out of the penstock into the downstream river.
Here's a close-up of the turbine and the generator. So once the water travels through the penstock, the force of the water pushes the turbine blades, which spins the bottom of the wicket gates, and it turns the turbine generator shaft. In response, the generator itself spins, and because there is magnets and copper coils, the copper coils will spin inside of the ring of magnets, and this will create an electric field that produces the energy, the electricity.
Specifically, when harnessing energy from moving water, there's a physics aspects behind it. Dams work in a special way to harvest the energy of moving water. With dams, water usually starts on top of a hill or waterfall before going through a dam. Once in a dam, the water has potential energy because it's on a higher elevated land. Since gravitational potential energy is mgh, water has more potential energy when coming from a waterfall or hill. As water falls at the dam, the potential energy turns into kinetic energy and is used to turn turbines to create energy. Power harnessed from dams depends on the flow and output of water. According to Do the Math, Dam power is equal to NTFGH, where G is gravity and H is the height, and F is the amount of cubic meters of water that flows through each second, and P, which is water density, which is around 1,000 kilograms per cubic meter, and N, which is the efficiency of the dam, which is usually around 90%.
Here's an example problem. So a hydroelectric power facility converts the gravitational potential energy of the water behind a dam to electric energy. So what is the gravitational potential energy relative to the generators of a lake of volume 50 cubic kilometers, so a mass of 5 times 10 to the 13th kilograms, given that the lake has an average height of 40 meters above the generator? So to start out, we're going to want to use the potential gravitational energy equation. So mgh. So the mass of the lake is 5 times 10 to the 13th kilograms. We're going to multiply that by the gravity constant of 9.8. And we know that the lake has an average height of 40 meters above the generators. So our height would be 40. And so when we solve this, we get the final answer of 1.96 times 10 to the 16th joules of energy. For part B, it's asking if a quarter of the water is released and flows at 23 kilometers per hour, what is the kinetic energy? So for this, we're going to want to use the kinetic energy equation of 1/2 mv squared. So because a quarter of the water is being released, we're going to want to use a quarter of the mass. Then we're going to want to multiply it by the velocity in meters per second. So we're going to want to convert the 23 kilometers an hour to meters per second. And we're going to square that. And when we solve that, we get that there is 2.55 times 10 to the 14th joules of energy.
An example that we can use that goes more into depth about the power produced is that of the Grand Coulee Dam. So if you look up on the internet, you can find that the Grand Coulee Dam produces an annual amount of 21 billion kilowatts. So we can check this number by using the power equation, which is the height of the dam times the river flow times the efficiency, all that divided by 11.8. 11.8 is the conversion to the watt unit, and then you can find online the rest of the information, like the height, which is 550 feet, the river flow, which is around 140,000 cubic feet per second, and the efficiency, which is 35%. So you plug this into the equation and you get around 2 million kilowatts, and then you multiply it by 24 and 365 to get the annual amount, which is around 20 billion kilowatts, which is close to the 21 billion kilowatts that we found online.
Another real-world example is the Three Gorges Dam. It is the largest dam in the world in terms of generating capacity and is located in China on the Yangtze River. In terms of energy production, this dam has a maximum power output of 22,500 megawatts. It stands at 181 meters tall and 2,335 meters in length. Its reservoir is 1,045 square kilometers big and extends up to 600 kilometers upstream. The dam consists of 32 main power generators. There's 14 on the left side and there's 12 on the right when it was first built. And then in 2011, 6 more generators were added for a total of 32 power generators. This dam outputs around 85 terawatts per year.
There are quite a few disadvantages when it comes to hydropower. Hydropower plants are dependent on the water supply. So when there is a drought, for example, hydropower plants cannot produce as much electricity. Hydropower dams on rivers permanently change the natural ecology of large areas of land, upstream and downstream. When a dam is built, the resultant reservoir floods large areas of land upstream from the dam. The natural ecology of the river and adjacent land downstream is changed by the reduction in soil deposition. Dams also can impact water quality and flow. Reservoirs can have low dissolved oxygen levels in the water, a problem that can be harmful to fish and downstream riverbank habitats. Maintaining water flow downstream of a dam is also critical for the survival of habitats. Some fish populations, such as salmon, migrate upstream to reach spawning grounds before returning downstream. Dams can block fish from completing this natural migration process. Fish ladders or elevators may be built to help fish swim upstream. Fish traveling downstream can be helped with a diversion or even lights or sounds. Development of new hydropower resources can be very expensive because dams have been built at many of the more economical locations. New sites must compete with other potential uses of the land.
There are also many advantages to hydropower. One advantage is hydropower is a clean energy source. It is fueled only by moving water, so does not produce any emissions. Hydropower does not increase the level of greenhouse gases in the atmosphere.
Hydropower is also a renewable energy source. So the total amount of water in the hydropower system doesn't change at all. The moving water that's used to generate the electricity in the dam is also returned to the source from which it came, back downstream.
Hydropower is usually available when it is needed. Engineers can manage the flow of water through turbines to produce electricity on demand and control the amount of electricity generated.
It's also an economical way to produce electricity. The maintenance cost of hydropower facilities are really low. Once a plant is up and running, the water flow that powers it is free. The electricity generated by the hydropower facilities is the cheapest electricity in the country.
Dams create reservoirs that offer a wide variety of non-energy benefits to communities, such as recreational fishing, swimming, and boating. The reservoirs can also increase the property value of the adjacent land.
Hydropower facilities can help manage the water supply, providing flood control and a reliable supply of drinking water during droughts. Many of the dams were built for flood control originally, but the power plants were an additional benefit.
Hydropower dams are very safe and durable, built to last for hundreds of years.
And lastly, hydropower is a flexible energy source in meeting electricity generating needs quickly. So the hydropower plant can begin generating electricity within minutes of increased demand. So most of the hydropower plants can also provide reliable and dependable baseload power.
Although arguments can be made for keeping or getting rid of these hydropower mechanisms, no one can deny the impact that they have made for present-day society. New ideas are being put forth currently that will improve hydropower efficiency and promote a more eco-friendly environment. One such idea is that of regulatory process optimization. This encourages organizations to increase accessibility to data, which enhances efficiency and makes scientific advances more available to the public and other companies. This has been our presentation on hydropower. Thank you.